Alright, so we'll get right back into this. This is going to be part 2 of the Velleman kit build. We did the resistors in the last segment. Now looks like we're going to get into the diodes. Alright, so the first set of diodes are going to not be these Zener diodes. It's going to be this little guy here, little signal diode. Probably a germanium or equivalent. Just for fun, let's find out. I'm going to reach down here and grab my multimeter. And we're going to set it to the diode test setting. Is that reasonably visible? Let's tilt it up so you guys can kind of see the screen. There we go. Alright, and then we'll just test the forward voltage of this LED, or LED, good lord. Chris, what are you saying? Test the forward voltage of this diode. 0.5 volts. That says more to me that this is probably a germanium diode, although they tend to be in the 0.3 volt range, whereas this one, he's going to be closer to 0.7 volts. He's coming across at 5.3 volts too. Okay, so apparently silicone diodes are now testing out at 0.5 volts on my multimeter, so this is a silicone diode. Germanium diodes will test out at about 0.3 volts. So this little guy here, which is a 1N418, I should probably just double check the microscopic text on that. Yeah, it is a 1N418, and it goes into the D1 position, which is somewhere. D1, there it is. Okay. Polarity is important with diodes. I think I've done a little spiel about diodes before, but they only allow current to go into them in one direction, except for Zener diodes. I actually have a video on Zener diodes. So polarity is important with the diode. So we're going to match the little black pip on the end of the diode there with the black stripe on the schematic, or any other sort of polarity indicator, so that we make sure it's going in the correct direction. I remember I built a kit a little while back that was a traffic light that used a brilliant matrix of diodes that I tried to reverse engineer, and it just became a headache. I don't know who came up with it, but it was brilliant. It used a decade counter and a really convoluted series of diodes to redirect the signals from the decade counter such that it very accurately replicated the process of a traffic light functioning, including pauses between, the one light going red and the other light going red, and the pause on yellow, and it was really a very cool kit. Kind of wish I could build it again, because it was very fun to make. Anyway, so now we've just got a standard 1N4007 power diode. These are just standard stock dime a dozen, pretty much literally, diode. And wow, I really did not do very well on bending those leads. Wow, that is super messy. I am not pleased with that. Oh well. So that diode's just going to be messy. Oh well. Alright, and these have really thick leads on them because they can handle a rather prodigious amount of current across them, and voltage. The 1N4007s have a peak inverse voltage cutoff of 1000 volts, so you can put a rather astonishing amount of voltage differential across the back of these, and I just did something bad, I think. Did I rip the pad off of the thing, or is that just a dry solder joint? Huh. Hopefully I didn't just ruin that. That's on the ground plane. I'm going to do a quick continuity test to make sure that I didn't just really screw that up. otherwise I'm gonna have to do some improvisation. So there's that. Okay, it still has continuity to ground, we're good. Alright. Although, come to think of it, I should do one more test here. We're gonna go to the from the positive side, which is actually on that pad, to here. Oh. Helps if I actually pay attention to the polarity of the diode on the other side. Okay, we're good. So what I just did there was I checked to make sure that the current still was flowing through the diode appropriately, which it did, so we're all good. I'll be a little bit more careful trimming this one. There we go. Alright, so we'll move on to the Zener diodes, which are these guys. Now these guys don't fully block current going through them when they're reverse biased, and that's the way they're designed. They are designed to only allow current to pass through them when the voltage reaches a certain level. Now these guys are 5V1 BZX79C5V1. I'm assuming that means that it's a 5-volt Zener diode. I've never seen 5V1 as a notation before. But I'm assuming that it's a 5.1 Zener diode, if it follows the same kind of notation as resistors. When they say 2K1, that would be a 2100 ohm resistor. I don't know why I picked that particular value out of my head, but that's apparently what came out. Alright. But anyway, Zener diodes, once they reach the potential, reverse biased potential voltage, they then start conducting. These are used for voltage regulators. I'll be using one in a project later on involving these high CRI LEDs, where I will demonstrate, well, I won't demonstrate it, I'll be building a constant current driver for the LEDs, but I'll be using a Zener diode to regulate the voltage to the gate of a MOSFET that I'm using to regulate the current to the LEDs. It's a rather clever little circuit. There's the other Zener diode. There we go. Right there. So those were marked ZD1 through 4. And before I solder these on, I'm just going to make sure that the polarity is correct. And then we're going to go ahead and solder them on. Let's clean the tip of my soldering iron a little bit here. There we go. Now with diodes, especially these smaller glass package diodes, they are fairly sensitive to heat, so I'm only going to solder one pin as usual, make sure they're nicely lined up, but I'm going to give them plenty of time to cool between using the soldering iron on them. And try to use the soldering iron as quickly as possible. An interesting thing to note with soldering techniques is that when you are working with a temperature-sensitive component, it isn't necessarily a good idea to turn your soldering iron too far down. If you run into it, you may find yourself turning your soldering iron down so far that you have trouble getting the solder to flow, and then you're having to hold the soldering iron on the component longer than you would normally. So you end up exposing it to more heat than a brief exposure to a hotter soldering iron. That can be a somewhat delicate process to find a balance, but I personally find that 300C is a really good middling thing, unless I've got a super temperature sensitive component, and then I'll go for a lower temperature. But we're not going to worry about that this time around. I'll stick with 300C. Anyway, the next thing on the procedure here is the socket. So we'll just drop this IC socket in here. There we go. And as usual, I'm going to solder just one pin of the socket, like so. Get some pressure on it. Reflow that solder to make sure that the socket is nice and flush, and then we'll go ahead and solder the remaining pins. There's that forced air heating I talked about in my last video kicking in. Isn't it lovely and noisy? There we go. I try to alternate around so that heat doesn't build up in the plastic of the socket. Probably not super necessary, but never hurts to be a little careful. You're going to have to solder each of these pins anyway, so may as well move around to protect it from heat. Alright. Ostensibly you don't have to trim these off, but they're a little sharp, so I like to nip the ends off. Like that. They're still a little sharp, but they're not as bad as they would have been. There we go. Alright. How much time do we have left? Alright, so I think that's good enough for this segment of the project. We got the diodes soldered in, and we'll move on to the next stage of the project in the next video. If you like, give me a like down, the button that's over here somewhere. Subscribe here, that's very important to support my channel at the moment because of YouTube's changes. I'll put a video that YouTube thinks you like here, and some random playlist, probably the Kit Builds playlist, I'll put right there. So thanks for watching, ask any questions you have in the comments below, and I will see you in the next segment.